Question 14, sorry about my voice. A regenerative braking system allows an electric car to use its kinetic energy to charge a battery as the car decelerates. A car travels at 13 meters per second, decelerates to rest. The energy transferred to the car's battery during the deceleration was 73,900 joules. Calculate the efficiency of the braking system. I'm just giving you the mass. Okay, so we'll start by writing down the equation for efficiency, which is efficiency is equal to the useful energy over the total energy, where the useful energy is the energy transferred to the car's battery to charge it, right? That's what we want from this braking system. So that's just 73,900 joules. Don't forget to convert. And the total energy, well, where did you get the energy from? Well, it says it uses the kinetic energy to charge a battery. So the total energy was from the car's kinetic energy, which is just half mv squared, which is a half times by 1560 multiplied by its initial velocity squared, which is 13 squared. So you put that onto your equation, 73900 over a half 1560 times 13 squared. I don't have a calculator, so I'm just going to rely on the mark scheme. Sorry about that. That would give you apparently around 56% or 0.56. I would personally put my answer to three significant figures. So let's say you had 0.562, then write 0.562, just because it's given all the values to three significant figures or more. So you want your answer to be to a minimum of three significant figures. Okay, let's continue. Drag forces act on the car as it moves through the air. State how the drag forces vary with the velocity of the car. Well, you should all know that as the velocity increases, the magnitude of the drag force will also increase. So as the velocity increases, the magnitude of the drag force is also increased. Why is that the case? Well, let's consider air resistance, for example. The faster your car, the more collisions it has with the air molecules. And every time it collides with an air molecule, it exerts a force on the air molecules, right? Because there's a change in momentum and forces change in momentum over time. So we know from Newton's third law that if the car is exerting a force on the air molecules must exert a force on the car in the opposite direction. And the faster you are, the more air molecules you are applying a force to. So the more air molecules that will apply a force to you, so therefore the drag forces or the air resistance will increase. The graph shows how the efficiency of the braking system depends upon the initial velocity of the car for initial velocities in this range. Explain why the efficiency of the braking system varies as shown in the graph. Or what we could see clearly is as the initial velocity increases, the efficiency decreases. Why is that the case? Well, we're going to use our answer for part I to help us with this. And this is generally the case. Your answers from part I or II generally help with the next part of the question. Not always, but generally. So what we're going to start off by saying is a higher initial velocity will mean there is larger drag forces acting on the car. Obviously, if there's more drag forces acting on the car, more work is done against the drag forces. What is work done? Energy transferred, i.e. more energy is transferred to the surroundings due to the drag forces. So more energy is transferred to the surroundings, i.e. more wasted energy. So now you have more wasted energy if your velocity is larger. So we're going to say for larger initial velocities, there is a larger proportion of wasted energy. We're going to say that efficiency equals useful over total. Hence, the efficiency will be lower, right? Because what is the useful energy? It's the total energy. Useful energy is the total energy minus the wasted energy. But now you have more wasted energy. So that's what I mean by there is a larger proportion of wasted energy. So yeah, this should get you 4 marks. A Galilean thermometer consists of a closed glass cylinder containing a liquid. In the liquid, there are several identical sealed glass bulbs as shown. Attached to each bulb is a metal disc labeled with a temperature. Each disc has a different mass. As the temperature increases, the density of the liquid decreases. This can cause the bulbs to move within the liquid. Explain why a particular bulb will float until the temperature of the liquid exceeds a certain value. Well, first of all, why would a bulb float to begin with? Well, let's consider the forces. A bulb will float when the forces are balanced, i.e. when the weight is equal to the upthrust. If the upthrust is larger, then obviously it will rise. If the upthrust is exactly equal to the weight, it will just stay where it is. So what we're going to say is the bulb floats initially as there is no resultant force. Always try to talk about resultant forces when you're talking about movement, i.e. something sinking or moving or accelerating or rising. So let's say why is there no resultant force? This is because weight is equal to upthrust. Where upthrust, let's define upthrust because we're going to have to use this definition later on, as you would see. Also, it's a 6-mark question, so there's no harm in writing as much detail as possible. This is because weight equals upthrust, where upthrust is the weight of fluid displaced. Now let's talk about what happens as the temperature exceeds a certain value or as the temperature increases. As the temperature increases, the volume of the fluid also increases, right? Thermal expansion. Therefore, the density of the fluid will decrease because we know from the equation P, density is mass over volume. We know that density is inversely proportional to the volume. So if the volume of something increases, the density will decrease. So because there's a less dense fluid, therefore, upthrust or the upthrust acting on the ball will also decrease as upthrust is depends. Okay, how do I phrase this? Let me think. Therefore, the upthrust acting on the ball also decrease as upthrust is the weight of fluid displaced, and the weight of the fluid displaced will decrease because weight equals m times g, which is equal to the density times volume times g, and the density of the fluid has decreased. Something along those lines. I probably phrased this really awkwardly. I'm sure you could do better. So now we said that upthrust has decreased. So now weight is larger than upthrust. So let's talk about resultant force again. There is a resultant force acting on the bulb downwards. So it will accelerate downwards / sink. I think this should get us 6 marks. Hopefully I didn't miss anything. Okay, so a student is flying a kite. The kite is held in equilibrium by a string as shown. The weight of the kite is 24 newtons and the wind exerts a force of 70 newtons at an angle of 43 degrees to the vertical as shown. Determine the magnitude of the tension in the string by using a scaled vector diagram. Okay, so any question involving a scaled vector diagram, you have to start it by thinking of a scale. And I'm going to say either 1 centimeter is equal to 10 newtons, or if you want the best results possible, you could probably do something like 1 centimeter is equal to 5 newtons. This might just about fit, or it might be too big. I'm not sure. You would have to do some draft measurements and see. So let's assume this is our scale, which is fine. You'll get the full marks. That would mean that 70 newtons is equal to or corresponds to 7 centimeters. And 24 newtons will correspond to 2.4 centimeters. So now we draw the scale diagram. We'll start with the 70 Newton force. So we're going to have to use a protractor. So use a protractor and measure 7 centimeters going at an angle of 43 degrees. If you don't know how to use a protractor, then learn how to use one. You could just like watch YouTube videos. It does require a lot of practice, to be fair, to draw these really accurately. Otherwise, you could make a silly mistake. And even if you're off by like 2 degrees, sometimes even 1 degree, that might be enough for you to not score full marks. So we drew the first one, and this is 7 centimeters. Now let's draw the second force, which is 24 newtons, directly downwards. You need to make sure that the tail of your second vector has to be touching the tip of the first one, because you always draw your vectors tip to tail. So we're going to draw 2.4 centimeters going down like so. And then finally, your resultant vector is always from where you started towards where you ended. We started drawing here and we ended here. So we draw a straight line like so. And then we'll use like a ruler, which we measure at eye level, to measure the length of this. And then if you did this properly, apparently you would get 5.5 centimeters. So you would have got 5.5 centimeters. And we know that 5.5 centimeters using this scale corresponds to 55 newtons. So the tension is 55 newtons. Okay, the student wants to determine the tension T in the string. She attaches a mass holder to the string. The student adds known masses to the mass holder until the kite is in equilibrium and part of the string becomes horizontal as shown. So it's in equilibrium. So the key thing we take from this is the forces are balanced. There is no resultant force. The student takes a photograph of the arrangement. Describe how the student can use the photograph to determine T. Well, the forces acting on this are the weight of the mass holders and the tension from the string. And we know it's in equilibrium, so we know that the forces are balanced. So let's consider the vertical forces because we have a reference, we have the weight. Horizontally, we don't have anything to compare it with and to say, oh, this is equal to that. So we're just going to consider the forces vertically. So vertically, you have weight downwards, but you also have the vertical component of your tension. Well, this is T, and we want to draw a right angle triangle, and this is theta. This will give you T sine theta. So let's put this into words. So we're going to say, for the system to be in equilibrium, I don't know how to spell, the forces must be balanced. Therefore, the weight of the mass holder masses must equal to the vertical component of the tension. Let's write that down in terms of the equation. So weight is equal to T sine theta. I don't have a theta symbol on my keyboard. Therefore, the tension is equal to weight over T sine theta. Oh, what's going on? It's so ugly. Okay. Where the weight of the mass and mass holder equal to M times G. But it's not enough just to say do this. You also have to say what measurements you're going to take. Well, obviously we need the angle. So we're going to say using a protractor. And you always have to mention the equipment you're going to use on these sort of describe the experiment question. So using a protractor, measure the angle theta, which is the angle between the horizontal and the string or the tension. Work out the weight using W is equal to mass times G. The tension will be mass times G over T sine theta. Good. I think that will get you 5 marks. All right, and this, by the way, this sort of thing where you have like a mass downwards, like suspended downwards, and then you have like a string at some angle. Sometimes you have more than one string. Just know that the forces vertically are balanced, and you're going to have to use this to make some sort of equation. So the forces up have to equal to the forces down. Let's continue.